Hey guys, and welcome to our 7.2 and 7.3 review lesson. I'm going to go through everything we've done in these two sections, maybe 1 to 2 problems each, just so we don't forget this information over the long weekend. The first thing we did is we identified vertical asymptotes of rational functions, and then we talked about how the domain is related to those. So we're going to start with that. Number 1 is g of x equals 3x over 5x minus 2. Remember that we can never have the denominator of a rational function equal 0. And for our purposes, when that happens, we generally have a vertical asymptote there. So to find the vertical asymptotes, we set the denominator equal to 0 and solve for x. So this first one, 5x minus 2 equals 0, I'm going to add 2. So I have 5x equals 2, and then divide by 5, and I have x equals 2/5. So I have a vertical asymptote at x equals 2/5. Now, because 2/5 is what makes my denominator equal 0, it is undefined at that value. So my domain is the set of x values such that x does not equal 2/5. All right, let's move on to number 2. F of x equals negative 2 over x squared minus 6x minus 16. So we're going to set our denominator equal to 0. This one is a quadratic function, so we're going to need to factor this. This is a trinomial, and we know trinomials factor to two binomials. The first two terms will just be x and x, since our first term here is x squared. So then we need to determine which factor pair of 16 has a difference of 6. Since it's negative 16, we think difference. So we could take 1 times 16, we could take 2 times 8, or we could take 4 times 4. Looks like 2 and 8 are the ones that have a difference of 6. Because it's negative 6, I'm going to write x minus 8 and x plus 2. Okay, now we use our zero product property. And we set each of these equal to 0 and solve their individual equations. So on the left, I will have x equals 8, and on the right, I will have x equals negative 2. So in this case, I actually have two vertical asymptotes. One is at x equals 8, and one is at x equals negative 2. So for my domain, I'm going to write the set of x values such that x does not equal 8 or negative 2. Okay, let's move on to graphing. So if you remember, when we were introduced to rational functions, the parent graph had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Let me draw that just for fun. So here is your vertical asymptote of the parent graph. No need for you guys to draw this, I'm just reminding us. And this is your horizontal. And then remember, it had the points 1, 1 and negative 1, negative 1. And those are kind of the points we use when we graph the transformed function. And this was a hyperbola. It has the two curves in the opposite sections. Okay, so what we're going to do when we encounter any function is identify the transformations that have been applied to that parent graph, identify the asymptotes, and then we're going to find one point on each curve to graph it, and then we'll give the domain, range, and end behavior. Okay, here we go. The transformations in this one, remember that we have our general form is g of x equals a times 1 over x minus h plus k, where a tells us our vertical stretch or shrink or reflection over the x-axis, h tells us right or left, and k tells us up or down. So my a value is 2, so that means I have a vertical stretch by 2. My h value here is actually negative 3, because remember, it's always x minus h, so we change the sign, which means I'm moving left 3. And my k value is plus 1, so I'm moving up 1. Because I have moved left 3, my vertical asymptote is now at x equals negative 3. And I'm going to graph that. And because I moved up 1, my horizontal asymptote is now at y equals positive 1. Okay. Now I can actually identify my domain and range from here because those asymptotes tell me what values are excluded from my domain and range. So my domain is the set of x values such that x does not equal -3, where my vertical asymptote is, and my range is the set of y values such that y does not equal 1, where my horizontal asymptote is. And the final step I do is I graph the 2 points that I need, the one on each curve. I use my a value to do this. Remember those 2 points on our parent graph that were right one, up one, left one, down one from the intersection of my asymptotes. Well, now because it's vertically stretched by 2, instead of going right one and up 1 unit from my intersection of my asymptotes, I'm going to go right one, up 2, and there's a point. And then I'm going to go left one, down 2. And those points are always symmetric from your intersection of your asymptotes. And then you draw your curves and they approach your asymptotes at the ends. All right. So your end behavior for rational functions, the end behavior is as x approaches positive infinity. So as we look to the right end of our graph, what are our y values approaching? And with the beauty of a hyperbola is that your y values are approaching your horizontal asymptote. So over here where x is approaching positive infinity, whoa, sorry about that. X is approaching positive infinity right there. Our y values, these are going toward our asymptote. So that's at 1. Y approaches 1. The same thing happens on the other end as x approaches negative infinity. On this end, our y values are going toward our asymptote at 1. Okay, so I'm going to go a little more quickly when I graph the next one. But before I graph this next one, this is one of those that we have to use long division to rewrite the function in transformation form. Oops, I forgot these parentheses there. Okay, so g of x equals -3x plus 15 divided by x minus 4. So I am going to do long division and put -3x plus 15 in my house and x minus 4 on the outside. And I ask myself, what do I take times x to get -3x? And that would be -3. And I take -3 times x, and I write that here, -3x. -3 times -4, and I put that right here. Then I subtract those. This would change to positive, this would change to negative, and I get a remainder of +3. Remember when we do division, we write our solution as quotient plus your remainder over your divisor. And oftentimes we switch the order so it looks like our transformation form. So if I did it in this order, my quotient would be -3, and I'd have plus my remainder 3 over my divisor x minus 4. And you can switch that order to help you identify a, h, and k if you would like. Doesn't matter. Okay, so remember your a, even though it's out here in front, it can be on top, which ours is right now. So your a is 3, so that's a vertical stretch by 3. Your h right here is actually +4, so that's right 4. Wow. Yeah, okay. So that's my vertical asymptote. It's at x equals 4. I'm going to go ahead and put that right here. Okay, my k value right here is -3. So that means down 3. So my horizontal asymptote is at y equals -3. And that is right here. Okay, domain and range then. Domain is a set of x values such that x does not equal 4. Range is the set of y values such that y does not equal -3. And now the last part is using my vertical stretch to plot my points. So instead of going right one, up one, because I'm vertically stretching by a factor of 3 from my intersection of my asymptotes, I'm going to go right one, up 3, and left one, down 3. Well, I'm off my graph a little bit. That's okay. Kind of hard to draw them when I get you so close to the edge of the graph. Okay. That's all right. So there's our hyperbola. And if I could see more to the right of this graph, I would see my right curve coming down closer to my horizontal asymptote at -3. So your end behavior, both ends are going to approach -3. As x approaches positive infinity, y approaches -3. As x approaches negative infinity, y approaches -3. Okay, guys, I'm going to end this video because otherwise it's going to get super long and you're going to have to watch the next one, which is over 7.3.